Okay, so we just got done talking about the distribution of sample means and what that looks like and when it looks like that. So now the next thing to do is just like before, when we were working with proportions, is to think about how you could estimate a population mean. And we're going to use a confidence interval just like in proportions. So you know that in a population, there's a mean that exists, a standard deviation that exists, but you don't know what these guys are. Population is just too big, and pragmatically we couldn't find them. So what we do is we take a sample. Right, now this needs to be a good sample. It's got to be random. It's got to meet the 10% condition, and it needs to be large enough. With proportions, that meant that 10 successes and 10 failures had to exist within a sample. When you take a sample to estimate an average, you have to make sure that the sample is big enough to overcome the skew of the population. Now, the only way you can really look at the shape of a population is to take your sample and look at its shape. Okay? If the sample looks approximately normal, then your sample can be really of any size. But if the sample looks skewed, that probably means the population is skewed. So your sample needs to be bigger. A rule of thumb is that if you take a sample bigger than 30, you can almost overcome any type of skew, unless it's really, really skewed. All right, so that's kind of what we're going to do here. So once you take this good sample, you have an X bar and you have an S. Now, these guys are fixed. I'm sorry, they vary from sample to sample, but we know what they are. I thought I wrote that down somewhere. It's on the next page. Okay, so even though these guys vary from sample to sample, we know what they are. So we can use these to estimate this guy. Right? Because once we take a good sample, we know this. The distribution of X bars. You take every single sample of a given size, n equals something. You find the sample average, and you make a histogram out of them. Okay? If the sample is small, then you're not positive that the shape is going to be normal enough looking, so you don't really know about this. You can't use the theory behind this. But if the sample is big enough, then we're good to go. If the sample is big enough and it was taken in a good way, then the distribution of X bars, every single sample average, is plotted on a histogram. The average of all these averages is the population average. Okay? But the only way you can get that is to take all of them. That's the theory. We're only going to take one. But if you took all of them, the average of all the sample averages is the actual population average. Okay? The shape is approximately normal, and the standard deviation of this histogram, of this bell curve, is given by the formula sigma over radical n, where this standard deviation is the population standard deviation. We don't know that either. And so that's the dilemma. How do we estimate these guys when we don't know what they are and this is all we have? The answer, as you know, is to make a confidence interval. Right? So we're going to estimate the population average using a confidence interval. So try to estimate this. Take a good sample. Get those guys. And then we can use X bar and S to estimate this. Now, because we're using different sample sizes in our formula, instead of using a Z star like we did with proportions, we're going to use a T star, which gives us a better estimate of the 95% or whatever we're doing, because the shape changes as sample size gets bigger. You know, this guy right here, it gets better looking as the sample size gets bigger. When the sample size is smaller, there's more area in the tails than there is in the middle when you look at different sample sizes for X bar. Right? So this is kind of a technical correction for differences in sample size. Okay? But the formula has the same form as proportions. To estimate the average, we use the average we have as the middle, and then we make the margin of error, our T star score, with this other technical correction that we don't have to really worry about. But we need this thing called degrees of freedom, and it turns out the degree of freedom is 1 less than sample size. Okay, we're just going to have our calculator do all this for us. It's kind of beyond what we need to do. When you study statistics in your graduate programs, you can talk about that. And then we have our formula for standard deviation, just like proportions. But with that mean, it's standard deviation over radical n. We don't know this guy, so to estimate the population standard deviation, we use the sample standard deviation. And that's our formula for a confidence interval to estimate population average using our sample information. I'll do an example, but I don't want to make this video too big, so I'll get back to you.